Right, here's section 1.3, average rate of change and relative change. So two different things here that we're going to talk about in this lecture. All right, so first thing here, if y is a function of t, in other words, y equals f of t, remember t is the input, f is the function, then the average rate of change of y between time equals a and time equals b equals, and average rate of change, we've talked about that just means slope, right? And it's still the same, right? Change in y over change in t, delta y over delta t, just as we've discussed before. It can be also written like this, f of b minus f of a over b minus a. It still goes back to, your algebra days, y2 minus y1 over x2 minus x1. It's the same thing, okay? The units of average rate of change are of a function are units of y per unit of t. All right, so the top per unit of the bottom. All right, so here's an example. All right, using figure 1.30, this graph right here, estimate the average rate of change of the number of farms in the U.S. between 1950 and 1970. All right, so we've got a problem like this. Again, it says estimate, right? So don't worry if the numbers are not exactly the same as mine when you look at this, but so let's see, 1950 is right here, right? Oops, 1950. So we're looking at that point right there. And remember, when we do average rate of change, we want 2 points so that we can plug into the formula that we just looked at above and find that slope, find that average rate of change. So let's create a coordinate point. So remember, this is t for time, and this is our y value up here. Okay, so we're going to create a coordinate point. So it's the x value in air quotes, right? So the t value is 1950, comma, and then we can estimate. So let's see. So this is 5. So I'm going to say, 5.5. Okay. All right. You guys see how we got that? It's right about here is 5.5. All right, we're going to create a second point. Remember, we need 2 points to create a slope. So the problem asked, again, between 1950 and 1970. So right here is 1970. So we go up to here. So this is 3. So I'm going to say 2.9, okay, just to estimate there. So our coordinate point is 1970, comma, 2.9, okay? From here, we just plug and chug, right? So the slope, the average rate of change, is the change in y over the change in t, right? Remember, it doesn't matter what order you put these in as long as you keep them in order from top to bottom, okay? So I'm going to do 5.5 minus 2.9 over, now since I did the 5.5 first, I have to do the 1950 first on the bottom. Okay, so 1950 minus 1970. All right, so that comes out to 2.6 over negative 20. Watch out for those signs when you're adding and subtracting. And if we punch that into a calculator, you should get negative 0.13. Okay? All right, so that's the average rate of change of the number of farms in the U.S. in millions. So negative 0.13, the units would be number of farms, or just, farms per year, okay? Now the negative, of course, represents a decline, right? So they're saying there's negative 0.13 farms per year. In other words, they're losing approximately 0.13 farms per year. Okay, and it's an average rate of change. Of course, you either lose a farm or you don't. You can't say you lost a fraction or a decimal of a form. That doesn't really make sense, but it's just to show what's going on. It's to show trends. Okay. All right. All right, so visualizing rate of change. So remember, rate of change just simply means the slope. Okay, so different ways to look at it. All right, so the delta y, remember that means the change in the vertical, right? F of c minus f of a in this case, right? They're saying here's these two x values, a and c. I don't know why they didn't use b, but that's okay. It's f of c minus f of a delta y, the change in the y values. And then over here, looking at the change in y versus the change in x. Okay? And again, that represents the slope of the line between those specific points. Even though what you can see is, the data here is represented by a curve. But for average rate of change, we're going to talk about the slope of the line between the 2 points. Okay. All right, here's another example. So they give us a chart here of tobacco production in millions of pounds per year. Right. So we start with 2003 all the way to 2015. All right, and you can think of this like these are your x's, these are your y's, x's and y's. Okay, so the question says, what is the average rate of change? So average rate of change again means slope. In tobacco production between 2003 and 2015, give the units and interpret your answer. Okay, so we're going to do what we just did in the previous problem. We're going to find 2 coordinate points, x comma y, and plug them into the slope formula and calculate. All right, so we said years is the x value and y is the production value here. All right, so let's see. We're going to do, well, first let's write out the points. So the first point is 2003, comma 803. Second point is 2015, comma 711. Okay, and we plug in. Here's our slope formula. Again, delta y over delta x, the change in y over the change in x. Okay, remember the order doesn't matter, but when you put the top numbers in, but you've got to keep the bottom numbers in that same order. So I'm going to do 803 minus 711. So that means since I did 803 first, I have to do 2003 first on the bottom. Okay, so this gives me 92 over negative 12. Punch that into a calculator and you get negative 7.7. Okay, so again, the negative slope, the negative average rate of change, of course, indicates a decline that's gone down. And that makes sense, right? We started at 803 and, from 2003 and 2015, 711. So it declined. All right, so delta y over delta x. Remember, y is production and x is years. So let's see, production is millions of pounds of tobacco. So negative 7.7 million, millions of pounds of tobacco, should have left more room, per year. So what they're saying is they're declining. This production is declining by 7.7 million pounds of tobacco per year on average. And of course, you can look at the data. It's not the same number every single year, the decline, right? Even actually some years it went up. Okay, but this is at an average between 2003 and 2015. All right, let's see. So let me clean this. Oops, let me clean this up a bit. Okay. Part B, during this 12-year period, so of course all over the data they gave you here, are there any 1-year intervals in which the average rate of change was positive, right? So it kind of looks like a pain. It's like, oh, wow, we got to, calculate all these slopes between every group, every 2 years or every year, but you really don't, right? We can work smarter and not harder on this one. We can just look at the production, right? We can tell right away from 2003 to 2004, that's a positive increase, right? And that's, of course, going to be every time. Every time you add a year, it's a positive increase. So that means our delta y is always going to be positive, right? So all we have to do is look at these delta x's here. Okay, I'm sorry, my apologies. The delta x's are positive. We have to look at the delta y's, okay, the change in y. So all we have to do is look at where the production increases from year to year. So look at the numbers. So 803 to 882, yeah, that's a positive increase, isn't it? All right. So the average rate of change is positive from 2003 to 2004. Okay. But from '04 to '05, that's definitely a decline. '05 to '06, that's positive, right? 2006 to 2007, that went up. 7 to 8 went up. 08 to 09 went up. Let's see, that one went down from 09 to 10. 10 to 11 went down as well. 11 to 12, that went up. 12 to 13 went down. 13 to 14 went up. Oops. And 14 to 15 went down. So there we go. Those are the 1 year intervals in which the average rate of change was positive. All right. Okay, so another thing we're going to talk about as far as the shapes of graphs and analyzing graphs here is concavity. So look at the word concavity, concave, right? You've heard that word before, hopefully. Concave means curved, all right? Okay, so when looking at graphs, okay, we're going to be looking just like, if this is so here's the x-axis and here's the y-axis. If your graph is shaped like this, if the curvature faces upward, right, that's concave up, okay? And of course, same thing over here. Here's the x-axis, here's the y-axis. In this one, the curvature is facing down, right, on each of these, okay? So that's concave down, okay? And you'll see, once we start talking about derivatives, how the first derivative and the second derivative tell us about increasing, decreasing functions and the concavity of our functions as well. But we'll see that later. All right, so here's an example. Here's a graph down here. The question is, which pairs of consecutive points, so next to each other, is the function graphed? And then there's different situations here. So we want increasing and concave up. So actually, I'm going to color code this. Let's look where the graph is increasing first. Okay, we can see increasing from A to B because the y values are getting bigger, right? And then also increasing from D to F and increasing from H to I. Again, increasing means the y values from left to right are getting bigger. Okay, so that's increasing. Let's look at decreasing. Where is this function decreasing? So that's just where the y values are dropping. So from B to D we're decreasing, and from F to H we're decreasing. Okay? So now what we've got to look at is the concavity. All right? So concave up. So concave up again means like that, right? Or it could also be like that. The curvature is facing upwards. Okay? All right, so let's look. Increasing, so we're looking at the pink ones we drew in there, and concave up, that curvature up. So I know it's a little hard to see, but you can see from D to E, we have that curvature up, right? I'm sorry, let's see. So we're looking at increasing, right here from H to I as well, that curvature faces up. Okay, so the answer there is from D to E and from H to I. Okay. All right, part B, increasing. So again, we're looking at the pink ones and concave down. All right, well, we can see from A to B, the curvature is facing down. And we also look right here from E to F, curvature is facing down. All right, and that looks like it. All right, and then now we're going to look at decreasing. So we're going to look at the blue parts now. Okay, so actually I'm going to clean this up so we can see better. All right, so we're looking at the blue parts now. All right, decreasing and concave up. So we can see right here, decreasing, decreasing, and the curvature is up from C to D. And let's see, does that happen anywhere else? See, now from G to H, I don't know. That's kind of a tough one, right? Let me get rid of that little line there. It looks like it might be slightly curved. It's hard to tell. Honestly, on a test, I would make sure I give you a nice clear graph. So we're going to say this one looks slightly curved upward, and still decreasing, right? So we'll also say from G to H. Okay. All right, and then decreasing and concave down. So we can see from B to C, the curvature's down, and from F to G. Okay? All right, so make sure you get those terms clear in your minds. Increasing, concave up, increasing, concave down, decreasing, concave up, and decreasing, concave down. Okay? Alrighty, moving on here. Okay, distance, velocity, and speed. Average velocity equals the change in distance over change in time, right? So velocity, we understand that as speed. That's what we normally talk about. Like, think about when you're driving down the road, you're looking at your speedometer, and that's telling you miles per hour, right? Distance per time. Okay? All right, so here's an example. Find the average velocity of the grapefruit. Oh, this is height of the grapefruit above the ground t seconds after it's thrown. On the interval from time equals 4 to time equals 6, and explain the sign of your answer. In other words, positive or negative, and what does that mean? Okay? All right. So from 4 to 6, right? Again, we're going to create a excuse me, a coordinate point. So 4, excuse me, comma 150, and 6, comma 30. All right, and we plug in again to our slope equation. Average velocity, average rate of change, all those things means slope. So delta y over delta t. All right, so the change in y is 150 minus 30. Since I did the 150 first on top, I have to do the 4 first on the bottom. Okay? All right, so we get 120 over negative 2. Again, watch out for those signs when you're adding and subtracting, which is negative 60. And the units are feet per second. So the grapefruit is falling between 4 and 6 seconds now. It is falling at an average rate of negative 60 feet per second. All right? So falling is the negative part, right? I mean, because when you throw something up in the air, it has to come down. All right? So they threw it pretty hard to keep it up in the air for more than 6 seconds, huh? All right, so again, that negative 60 just represents that the grapefruit is falling, is losing altitude between 4 and 6 seconds. Okay? All right. All right, so that's average velocity. Next, we have relative change. Okay, so in general, when a quantity P changes from P0 to P1, so P sub 0 right there means the initial or the beginning, right? Time 0. P1 just means after 1 unit of time. All right? Okay, so relative change in P. It's the change in P, delta P, over the initial amount. In other words, we would do P1 minus P0, right? So that first interval minus the initial value divided by the initial value. All right, so this relative change is a number without units and is often expressed as a percentage. Often, but you could also represent it as a decimal. Okay? All right, so let's do an example here. All right, the number of sales per week of a $75.99 pair of jeans is 25 pairs. The number of weekly sales goes up to 45 pairs when the price is reduced by 30.3%. Find the relative change in the weekly sales. So we need to find what's the initial value of these jeans and versus how many they sold. And let's find the first time unit, right? Value. All right, so it said initially they sell 25 jeans for $75.99. Okay. All right, so let's calculate that one. Probably should have calculated these before, right? So 25 times 75.99, 1899.75. Okay. Now we got a little bit of math to do here for this P1 here. So it goes up to 45 pairs, right? But the price has been reduced by 30.3%. Okay. So what is that price? It's not $75.99 anymore. Okay, we're going to do 70. Well, so first thing we should do to reduce it means we're going to, if we reduce it by 30.3%, so remember when we use percentages in calculations, we change them to decimals. So this will be 0.303, right? Okay. So what we're going to get here is we're going to say 1 minus 0.303 times the 75.99. Okay, so this part of the calculation right here represents that 75.99 reduced by 30.3%. Okay, reduced means subtract. Okay, so let's calculate all this. All right. All right, and this all comes out to 2383, and we'll estimate it not estimate, but round 0.43. Okay. All right, so from this point, we just follow the equation, right? The relative change in P is P1 minus P0 over P0. All right, so we just plug in the numbers we just got here. So 2383.43 minus 1899.75 all over 99.75. Now when you punch this into your calculator, make sure you use parentheses in your numerator. Okay, otherwise you will get the wrong answer because the calculator will do the PEMDAS, the order of operations, wrong. All right, so let's see, 2383.43 minus 1899.75, so that's 483.68 over the 1899.75, so let's calculate that. So this equals 0.2546, well, we can round that to 0.25, all right? And it said usually express it as a percentage, okay? So 25%, okay? So it's positive, right? So that means it's an increase in 25%. So even lowering the price makes more money for them, right? Because they're going to sell more units, okay? All right. All right, so let's see. Last section for today, 1.4. So let's see. Applications to functions of economics. So the cost function. C of Q. Q is the number of units. Okay. C of Q gives the total cost of producing a quantity Q of some good. Q, number of items. All right. So this little bit right here is important. If C of Q is a linear cost function, fixed costs are represented by the vertical intercept, in other words, the y-intercept, the b value, right? Remember mx plus b? Variable cost per unit is represented by the slope. Variable cost per unit is also known as marginal cost, all right? So same thing. Variable cost per unit and marginal cost are the same thing. Okay. All right, so this example says graph the cost function and label the fixed cost and the marginal cost. So here we go. Let's make a little graph here. Oops, okay, there we go. All right, so let's see. So this is cost function, and this is Q. All right, so we're gonna graph this, right? We always look at the y-intercept first. So 24,000, we can just put it anywhere on this graph, not to scale, of course. Plus 7Q, 7 is positive, that's your slope, your rise over run, right? So 7 over 1. So it's gonna be kind of a slow increase over time. Okay, so there we go. So it says label the fixed cost and the marginal cost. So here we go. The fixed cost is the y-intercept. And the marginal cost is the slope 7. Okay? So the fixed costs are $24,000. Oops. All right, and the marginal cost is $7 per item. Okay? All right. Let's see, so next is revenue. Revenue is how much money you take in, okay? And we'll see a little equation down here in just a minute for revenue. But for now, revenue function R of Q gives the total revenue, the total money taken in, received by a firm from selling a quantity Q of some goods. All right, so here's an example. We're gonna graph the cost function, it's the one we just did, and the revenue function on the same axes, and then we're gonna look we're going to analyze it. So I'm going to copy this. Okay. Oops. There we go. All right, and then we're going to graph so we graphed the C of Q, the cost function, that's the blue one. All right, so let's label it C of Q. And then R of Q, the revenue function, is 15Q. So in terms of mx plus b, the y-intercept is 0 on this one, right? So 0 with a slope of 15, which is bigger than 7. So again, this is not to scale, but it's going to look like that. It's got a bigger slope than the cost equation. So this is our revenue equation, R of Q. All right, and then they want to know for what values of Q, so these are Q down here, does the company make money? In other words, when is revenue bigger than the cost? When are they making more money than they're spending, right? Okay, so what we're going to do is we're going to look at where this intercept is, all right, that Q value. Well, it's kind of hard on this graph. If we graphed it on a proper axis or use a calculator, it'd be much easier to figure out, or just by looking at it, but we can figure it out algebraically. So that's where the two graphs meet. In other words, that's where these two are equal, these two equations. So we do 15Q equals, 24,000 plus 7Q. All right, so we do some algebra, right? We subtract 7Q from both sides. So we get 8Q equals 24,000. We want Q by itself, so we divide by 8. So Q equals 3,000 units. So what they're saying is after 3,000 units. So Q has to be actually greater than 3,000 units because they're breaking even at 3,000. Okay? So for Q greater than 3,000 units is when they're going to start making money. Okay? All right, so let's see. Like I said here, so here's the profit equation. Profit is revenue minus cost. Okay, revenue is how much money you take in. Cost is how much money goes out. What's left over is your profit. Okay, hopefully that's a positive number, right? All right, so here's an example. The figure below shows cost and revenue for a company, right? So let's see, part A, approximately what quantity does this company have to produce to make a profit? It's just like the one we did a second ago. We just look at the break-even point where the two graphs meet. So we're going to estimate, of course. It may not be exact. That looks like, I don't know, what, 320 to me? Okay. Let's see. So what company does this what quantity does this company have to produce to make a profit? So at the 320th item, they break even. So that means they're going to start turning a profit at the 321st unit. Okay. All right, and then part B, estimate the profit generated by 600 units. So right here is 600. So we're going to look at the cost and the revenue function values at that point, at that quantity. Okay, so R of 600, that means the revenue at 600 units. Let's see, that looks like, so this here is 2,000. So what does that look like to you? 2,400? Remember, we're estimating because of the graph. And then the cost at 600 units looks like about, what, 1,750? Okay. So then what we're going to do is we're going to simply subtract, right? All right, so profit at 600 is the revenue at 600 minus the cost at 600. So we got those two numbers there, 2,400 minus 1,750, and that's good. They're definitely going to make a profit because that's a positive number, and we can already see that by the graph, right? The revenue graph is bigger than the cost equation, the cost function. So this is a profit of 650. Pretty good. All right. Okay. Next, we have supply and demand curve. So you've all heard the term supply and demand, right? It's like anything that goes up in value. The more supply there is, in general, the lower the demand, and vice versa. So the supply curve for a given item relates the quantity Q of the item that manufacturers are willing to make per unit time for price P to which the item can be sold. The demand curve relates the quantity Q of an item demanded by customers per unit time to the price P of the item. Okay, so those are important to know. Equilibrium price and quantity. So equilibrium, equal, right? If we plot the supply and demand curves on the same axes as shown below, the graphs cross at the equilibrium point. The values P star and Q star at this point are called the equilibrium price and equilibrium quantity. Right? So again, that's just where the two graphs of supply and demand meet up. It is assumed that the market naturally settles to this equilibrium point, right? Because again, if the manufacturer produces too many, then the demand goes down. Too many, everyone has one, nobody wants it, right? But as we see all the time, when there's less of that quantity out there, people want it more, and they're willing to pay more, of course. Okay? All right, well, that's where we're going to stop the lecture today. Thank you very much.